Okay, so we continue in section 1.7, the precise definition of a limit. And we're going to do example 3 in this video. To review, we have looked at the two-step method for proving a limit. Number 1, you got to get your delta. Got to find it somehow, reasoning according to the definition, and delta must be a function of epsilon. And then we state a formal proof showing that that delta that we have chosen works. The intuitive definition of one-sided limits can be precisely reformulated as follows. Okay, so here's a left-handed limit. Limit as x approaches a from the left of f of x equals L. That's what we're defining if for every epsilon there exists a delta such that if x is between a minus delta and a. So we are imagining that, there's a number a out here somewhere. Number a. And then there's a small delta interval out here. And x is going to approach a from the left. Okay, now x cannot go to the right of a. Okay, x can't go out there. X is strictly less than a. But x is entering into and staying within and approaching a from within a delta interval to the left of a. Then something happens up here with f of x that it approaches L. It is within epsilon of L. And right-hand limit, we got something similar going on. There's a number a somewhere. There's a number a somewhere. And now x is going to be between a and a plus delta. So there's a little delta ball over here. X is arriving at a. It can't go to the left of a because x has to be strictly greater than a. But it's approaching a from the left, and that entails that something's happening up here with f of x. Or maybe it's down here. Okay, so we're going to use definition 4, the definition of a right-hand limit, to show that the limit as x approaches 0 from the right of square root of x equals 0. Okay, so we can imagine, the picture here. Here's a square rooting function. And as we approach 0 from the right, the function is converging on 0. Okay, so we have to get a delta. Okay, now this is it's not a linear function, so it's not just a simple matter of dividing epsilon by the coefficient of x in the linear function. Okay, we've got a nonlinear function here, square rooting function. Maybe you have an intuition about what delta is going to be. Let epsilon be a given number. Here a is 0 and L is 0, right? Okay, so we're trying to find the limit as x approaches 0 from the right of square root of x equals L. So the a is 0. The f of x is the square root of x, and the L is 0. So we want to find a number delta such that, according to the definition, okay, if x is between 0 and delta, okay, now that is what this says here because a is 0. Then this part, square root of x minus 0, the absolute value of, less than epsilon. Of course, that second thing, the then clause there, can be simplified. And you don't need that. You don't need to say minus 0, of course. And you don't have to, you don't need the absolute value bars because the square root function, f of x equals square root of x, cannot be negative anyway. So our task reduces to finding a delta so that if x is between 0 and delta, 0 less than x less than delta, then absolute x less than epsilon. Or we could rewrite this part. We could square both sides and say x less than epsilon squared. Okay, so now we have to find a delta so that if positive x less than delta, then just x less than epsilon squared. And so what we've achieved here is writing the then clause, the epsilon clause, okay, involving that. Okay, we've got an x here, so now since we've been able to rewrite it that way, the delta we'll be able to find. We arrive at the delta easily. This suggests that we should choose delta equals epsilon squared. Okay, so we've come up with our delta, okay, that we're going to use in our proof. Show that it works. Okay, so we're just going to show that we're going to be able to say all of that, and because we're going to be able to say all of that, we're going to be able to say this, and that's what we're required to do. So given epsilon positive, let delta equals epsilon squared. Now we're allowed to do that, right? We're allowed to let delta equal epsilon squared. You might be wondering, why do we get to do that? Okay, well, we just need to show that for every epsilon there's a delta. Okay, well, for every epsilon there's a delta. Just square the epsilon and you've got the delta. So if positive x less than delta, then, okay, square root of x is less than the square root of delta. Okay, so take square root of both sides. In other words, replacing delta with, okay, that's a crazy delta they've got going there. Script delta. Replacing delta with epsilon squared, because that's what we are hypothesizing it to be. We've got the square root of epsilon squared, which is epsilon. So now we have the conclusion, okay, on the assumption of this original black inequality, okay, square root of x is less than epsilon. And that's saying the same thing as this clause here that we're required to be able to say anytime we've got x between a and a plus delta. In other words, 0 between x and delta, because again, a is 0. And so all we have to do is kind of restate this in this way here. Everything that we've just said, we're just going to restate, and that will show that we have proven the limit. Okay? And so now, taking this clause, square root of x less than epsilon. Well, square root of x, that's the same thing as square root of x minus 0, which is the same thing as absolute square root of x minus 0, because square root of x can't be negative anyway. That's less than epsilon, and so now we have that second clause, the then clause of the if-then. And that therefore proves that since we're able to say this, we now can say this, that we do have this limit. We now have proven that the limit as x approaches 0 from the right of the square root of x equals 0. Okay. A reminder that the laws of limits, the limit laws, such as this one, that the limit of a sum is the sum of the limits, hold for one-sided limits.